All right. So I'm going to discuss the two imaging domains, the application and the two imaging domains, and we're going to see some of the existing applications. It's not possible to cover all of them in a session like that. You can see some examples about image translation, pose estimation from a vision, or the brain registration, classification, cardiac segmentation from the medical domain. Okay, first we're going to check the computer vision ones. So again, even for an individual domain, it's impossible to cover all of them. So we are going to skim through the most popular ones, most used ones, let's say, but do not consider this a survey. There are a lot of great papers in all of the domains and methods that are not showcased here. So let's start. We'll start with image translation. We move to face attribute transfer, which is a special case of image translation, but it's very interesting. We move to pose estimation, and we have another application also. I'm going to skim a bit quickly through the computer vision domain, so we can spend some more details, some more time in details in the medical domain. So starting with image-to-image translation, the most widely known method or model is the M-unit. So the M-unit pushes for more reductive design in models in general. They disentangle the content from the style. They have a special content code and vector style code. In the let me use the highlighter. Oh, no, I can use the annotation. Okay. So in the content part, there are after each convolutional layer, there's an instance normalization layer, so that we can remove any style information like texture, like illumination stuff. Then okay, then we have the style encoder. That's uses another building block that we examined earlier, the global pooling, global average pooling, that removes any spatial correlation and extracts the style code from the input image. So in the style part, the style encoder, we don't use any normalization. And another building block that we discussed earlier, the add-in the add-in module is used to re-encode the not to re-encode, sorry, to re-entangle the content with the style in the decoder into multiple layers and have the image reconstruction. So there is an implicit Gaussian prior in the style code. So we want our style distribution to match the one of an isotropic Gaussian. Also, note here that we may have a spatial content, but the content is not semantic. So if I choose randomly one channel from the feature map, and I will not be able to interpret 100% what I'm looking at. So, okay, another model that of image-to-image translation is DRIT. So DRIT is a successor of the unit or the cycle gun models. So the cycle assume that we have two images from two different domains, the X and Y. So cycle gun maps X and Y onto separate latent space. Unit assumes that X and Y can be mapped on a shared latent space, while DRIT here disentangles the latent spaces of X and Y into a shared content space, okay, called C, and an attribute space called A of its domain. So it's similar to M-unit in general, but uses unpaired data it needs to have a second domain. So MUnit can operate in a single domain. It needs to have a second domain. They use several losses, which is opposed to inductive design. So they use heavy learning setup bias, and they aim for content invariance using also discriminator during training. That can be risky. Yes, let's go to the augmented cycle gun. As we said, the cycle gun, the simple cycle gun maps X and Y to separate latent spaces. The augmented cycle gun is used mostly. It's concurrent with MUnit and SDNet. We're going to see SDNet in the medical applications part. It has a different motivation here. It's not like one-to-one translation, but it has mostly a one-to-many, one-to-many or many-to-many mapping translation, and the many-to-many mapping, one-to-many or many-to-many mappings translation is being realized as cycling over the original domains, augmented with auxiliary latent spaces. Okay, this was the typical image-to-image translation. A more specific case, the face attribute transfer. Very well known application is called TransGaga. It's a very cool name. Again, it's an image-to-image translation model, but the key points here are the content, and the key points actually are associated to facial features. So ideally, we can somehow translate our face from a human face to a cat face, like the expression, by sharing the content part, so sharing the key points. They're using VAE, the VAE models. They used unpaired data, of course, and their content is loosely semantic, and they use prior knowledge. And as I said, the key points that are associated with facial expressions, each key point is encoded into a different channel of the content. They also have a separation loss. Encourages the points, the key points, the learned key points to spread in the image, not be lazy and stuck up in the middle of the image. And also they use different encoders for the style and the content, just as MUnit or Treat. Okay, but that was one application of translating the full face expression. What if we want to actually transfer a content part? So the main problem with synthesis is that we spend capacity doing things that we know. Okay, for example, if I want to create a face with glasses, why should I spend capacity doing anything else rather than figuring out how to put the glasses on the face? So here, Mokadi et al. Created a model that copies, transfers the attribute, the content part that we want, for example, the glasses, or removes it if we want to remove the glasses from a face, or mustache, as you can see from the next example. So how? So given two images, they find what's different between the two images, and they create a blending mask and background texture, and then combine them. Of course, they have heavy regularization here, and also there's the dust bias that can be exploited, especially a dataset that contains only faces, and the face covers the majority of the pixels of the images. Okay, so let's move to the next part. Just a remark here about estimating mask and then combining. we're going to see, I'm going to say more interesting because it's more practical, a more interesting application in the medical domain, in the synthesis part. All right. So moving away from image-to-image translation, let's see how can we how this entanglement helps us in pose estimation. So rapidly, many researchers realized that the ability that the content that we can model the content as a latent variable that can be used for quantification and for solving actual vision or image recognition tasks. So an early approach was to use the simplest idea of what the actual the encoded content is. It's a landmark, as we saw earlier in the phase attribute translation. So they used an encoder and a true bottleneck representation for structural content, and the landmark points are encoded as Gaussian distributions at its I, j location, its pixel location, again 1 per channel, as we saw earlier. So we have two networks here, two autoencoders. The one network learns to extract these points, these key points, and the other one learns to extract style, the generic style of the image, using paired examples here, paired data. So this means that we have to, if we take one frame of a video with a human specific pose, then we have to take another frame from the same video, or augment at least the kind of frame to have two inputs for the two models and two parallel models. So surprisingly, this combination of networks is trained as a simple autoencoder with the perceptual loss, and the authors evaluate the accuracy of how close these landmarks are based on ground truth from label points, as opposed to the previous application of the phase attribute transfer, where the authors did not provide any quantitative result of how well are we learning the landmarks phase. Of course, again, we have a very high density bias in order to make it work, as images of poses have a well-defined position in a single object on a static background. Yes. So another application in pose estimation, is about stepping up the idea from landmarks, where essentially they're implementing as strobe Gaussians with a fixed standard deviation. In this paper, we have Gaussian distributions that have variable covariance matrix. So the model of Lawrence et al. Actually decomposes the pose and the appearance style, and encodes the pose as a content and the appearance as style, and employs heavily entangled encoders and decoders for this task. So the content is represented as a multi-channel feature map, where each channel corresponds to a specific body part. Okay, and since there's a fixed number of body parts, here we have strong data bias induced in the learning process. Also, a Gaussian distribution is applied, as I said earlier, to its feature map to remove any style information, while also preserving the spatial correspondence. The corresponding style information is extracted from the encoder features using average pooling again. As you can see, using average pooling is very common when we want to extract a style. Also, the style vectors do not correspond to the global image style, since they are applied to specific content parts during the decoding, so to specific body parts during the decoding. And also, disentanglement here is encouraged with the transformation equivariance loss. Equivariance loss, it's a learning bias. This loss ensures that the spatial transformation, such as translation and rotations, affect only the content representation, while the intensity transformations, or the illumination transformations, or anything that's related to the style affects only the style encoding. So about some other applications, a very good example is the image generation, specifically the control image generation. The controllability part is based on the disentanglement. As you appreciate, there's a considerable interest in being able to have some control over what semantic information is available within the content and emphasize spatial object disentanglement along the lines of the previous paper that we discussed. Of course, one should be able to learn the semantic information with as weak labels as possible, so that we don't need many labels for every sample that we use. So the recent paper for Pablo et al. Follows the idea of using attention as a semantic driver and uses a semantic attention module that separates information in semantic masks and then adaptively creates content. They use a two-step generator here, where the first generator has a specific task like creating the background, while the second generator has the task of blending the foreground with the generated background. You can see some very impressive results here. All right, so moving to the medical image analysis applications, we should note here that medical applications can benefit a lot from disentangled architectures due to the lack of available data. As Otto said earlier, in a response, we should not assume an infinite amount of data because, for example, in the medical domain, we don't even have enough data to train deep models. We struggle. So disentanglement is an excellent solution of exploiting less data and achieving better results. So in medical image analysis, we have training. We have the following situation. So we have training data bias in situations like for example, the data are acquired from similar scanners, but they need to be tested in a wide variety of scanners. So we have the acquisition shift, or we can have like one pathology it's much more frequent, and we have a very rare pathology that we need to test on. So we have population shift, and also we have data come from few institutions. Okay, so before we start with the applications, I would like to note here that in the computer vision domain, there have been many frameworks, many libraries, many packages developed through the last 7-8 years that help young researchers contribute much quicker, understand the research, be able to implement models, experiment, so contribute to the actual research community. But in the medical domain, we had always a problem of implementing relative models, implementing our theories, and exploiting deep learning in general. So the last 2-3 years, there are excellent frameworks, packages developed. So all of them are open source, and I would like to share 4 of them here. One of them is Gandalf. It's mostly at least the current version is mostly oriented around segmentation, regression, and classification. Medical imaging, MONA is a very well-known framework, has end-to-end training workflows in much more diverse applications in the medical domain. It's also Medical Torch, is the oldest one that have ready-to-use loaders, preprocessing modules, and also it's Torch.io that has extra tools for reading, preprocessing again, how to sample data, how to augment them, not only in 2D but also in 3D space. You should check all of these frameworks, as they will help you a lot as you get familiar with disentanglement in the medical domain. So they are highly recommended. Okay, let's go to the content style in medical imaging. Let's see how do we associate the content style in the medical domain. So we discussed about how content style disentanglement, what content style disentanglement is and how it's applied to the computer vision tasks. And here we want to showcase that with the image, that assuming that we have a representation of a medical image here of patient, what can be different is the scanner, acquisition scanner, or what can be different is the anatomy, so a different patient. So we want to do a one-to-one mapping. As content, we use the anatomy. We use the anatomy as content, and we use the appearance of the imaging modality as style. So both the presentations capture some semantics, and they're useful for several imaging tasks in this domain. Again, it's impossible to share everything to survey the applications, so we're going to focus on segmentation, medical image segmentation. It's a very challenging domain. Also to synthesis, since this is one of our arrows that can help us confront the absence of data availability. Then image registration, when we have different imaging representations from the same patient, and we want to combine them, and also some other applications. Let's go to the segmentation, applications. First of all, we would like to highlight SDNet, so it's spatial decomposition network. That it was the first application of content style disentanglement with a spatial and semantic content in the medical domain. It has been tested. Originally, it was tested in the cardiac domain, so cardiac MRIs, cardiac CTs, but it has been also tested to other data sets. Its application is in semi-supervised learning. So as we disentangle the content, the anatomy, we don't need ground truth information about every sample we use. They use the authors a discriminator for the samples that don't have semantic annotations, and then the anatomy and the appearance are reentangled, and we reconstruct the input image. So the anatomical representation can be used for segmentation, or both of the representation can be used for regression to some electronic health record markers. And of course, since we disentangle the anatomy from the appearance, from the modality, we can use almost any modality. As I said earlier, SDNet has been tested with MRI and CT scans. In order to reentangle the content, the anatomy with the appearance, they employ employ film, as we saw earlier in the building blocks. But there's also a version with the add-in module. So as I said earlier, this is concurrent with the unit and the augmented cycle gun. That's the first application in the medical domain. We can also segment and reduce the artifacts. A very good example here is by removing the artifact. Okay, we first of all mean that we want a higher resolution image, let's say. So here in the vertebra segmentation task, we can do that in a supervised way. So we have cone beam computed tomography images. Okay, but we don't have they're high resolution and precise images, but we don't have enough ground truth for these CBCT images and vertebra annotations. So we would like to learn how can we synthesize, how can we arrive to a high precision, high resolution and precise image from a CT scan of the same image. So we want to disentangle the appearance, the image information into two different representations. One will encode the actual intensity of the input, and the other will encode the artifacts, just as encoding noise. Here, since we have some annotations, semantic annotations, we are going to employ SPADE during this transition, this learning, going from the CT to the CBCT domain, and we're going to condition the imaging process with SPADE in order to generate this high resolution image. Okay, after segmentation, we have image synthesis. It's a critical task for.
May I suggest we accelerate a bit, just a little bit, because we are very tight now.
Yes, of course. So, okay, we're going to very quickly see three applications. The first is the image synthesis in the retina. So, for example, we have fluorescein fundus angiography, which is an effective and necessary imaging technology for many retinal diseases. However, there are certain drawbacks, like it's an invasive operation. Okay, the dye that they're using is harmful. And also, there are some side effects. So here we want to enhance the retina fundus by including vessels and granular structures through synthesis. So now, as we said from the CT, going from CT to the CBCT, now we want to go from the fluorescein fundus to the fluorescein fundus angiography. So we disentangle domain features, so we disentangle domain shared structure and domain independent appearance. Again, it's like extracting the content and the style. We fuse the two features for the generation, and we use, if you recall, we discussed about cycle consistency as a loss. So here, the cycle consistency means that if I go from the input to a generated output, and then do the same procedure, returning to the initial domain, I have completed the cycle. So I can always use a pixel-wise similarity to compute the differences, how correct or wrongly do I reconstruct the image. So another synthesis approach is about how to disentangle the pathology of from the anatomy. Here we discuss about the pseudo-healthy image generation, and we learn to separate the pathology from the anatomy. This can be done into both paired and unpaired settings. As you can see, we can use in in the both paired and unpaired settings, and also we can use in the paired setting segmentations, or if we don't have segmentation, we can use a discriminator. Also, we discussed about causality and its inclusion in the disentanglement domain. Here we can see how can we synthesize with interventions. So we have the causal image synthesis, a special case of conditional image synthesis, which is performed using structural causal models. Structural causal models are actually graphs that describe the relations between disentangled attributes, disentangled representations. Here they use normalizing flows, and in a special case of brain MRI, they encode attributes like the sex, the age, ventricular volume, and other relevant attributes, and they use conditional VAEs. So the conditioning part here, is the normalizing flow. They use normalized flow to condition the VAE. So they use a graph of the attributes to synthesize inputs by intervention. So synthesize inputs by altering a specific attribute. Okay, we can go to image illustration. Kin et al. Propose an unsupervised and modality agnostic method for anatomy registration. They convert a multimodal problem into a monomodal one. So as you can see, for its input of a different modality, they use an M unit like structure to extract the anatomy and the modality representations, and they use a module that employs bidirectional registration as we compute the disparity for both inputs, and we're not warping one domain to the other. As you can see here, we try to extract the anatomy denoted with S, ZS, and we register the two anatomical representations together. Also, we can have registration as a module, not as a whole task. So we can have it as a component. We can use it for any partially equivariant task, for example, segmentation. So we can initially disentangle, assume we have two different modalities. Here they have CineMRI and LG. So you can disentangle the content from the style. You can use it to anatomical representations. You can use, so this is not a bidirectional alignment, it's a single directional alignment. You can use spatial transformer network to align the anatomy of one input to the other. You can fuse the anatomical factors and use them as input to your segmentor. Also, this work supports temporal slicing, slice pairing between inputs, which is learned dynamically, and has been tested into cardiac and abdominal inputs. Finally, we have what we call domain generalization. Actually, these works could fit into other tasks, but their contributions are very, very interesting in terms of generalizing models. So that's why we created a separate category for them. The first work here is used to generate intermediate representations. So we assume already disentangled content, already disentangled anatomy. So we have the factors extracted. We can perform arithmetic operations with them. We can mix and match them in order to generate and then re-entangle them with the appearance, the modality factors, in order to generate representation, unseen representations, bridging population representations. You can see this paper on Wednesday as an oral presentation. You're welcome to check the details there. Also, we have the domain adaptation using meta-learning, it's a very hot topic. So generalizing deep models to new data from new centers is a challenge. We have large domain shifts between domains. Here the authors use a meta-learning approach. They combine meta-learning with disentanglement. So the trained data are split into meta-train and meta-test sets in order to simulate the domain shifts that exist in seen and unseen data. And also they use, in terms of disentanglement, they disentangle the input into anatomy, appearance, and also domain. Last, we have generalization through style augmentation. So here we generalize the model in terms of the style. Wagner et al. Propose a GAN-based augmentation technique. It's for histopathological images. So the histology patches mapped from one medical domain to another. Of course, it's inspired from image-to-image translation. And here, what we achieve is to preserve the histological structure and learn representation of the style domain that matches a Gaussian prior. So here's another bias, another building block that we discussed earlier. Anyway, I'm going to leave the floor to Dr. Alison O'Neill to present us the applications of disentanglement in the electronic health record domain.
Thanks, Firas. Great. So I'll just share my screen. Do you see my slides?
Yeah.
Yeah, fantastic. Cool. I'll just take 10 minutes to talk through electronic health records. Of course, we all believe that the future is multimodal. So we're looking beyond imaging to other data that you would find in the patient record. So here's my first possibly rhetorical question. It's often said that a picture is worth 1,000 words. Do you think that's true, or is it false? Well, if we take a look at an example of a chest X-ray, which I've taken from the MIMIC CXR dataset, we can see that for an image of several thousand pixels, actually in 62 words, a radiology report can capture most of the important findings and can come to a clinical conclusion, even with extra information that you wouldn't be able to get from the image, but that you know from examining the patient beforehand. And if we take a look at another example, which is an example of a typical patient history, in this case, it's an ankle sprain that they're reporting on, you can see that the imaging part of this report is actually just this yellow sentence here. And there's a lot more going on in just 346 words that tell you a lot about the patient. So there's a history of the ankle sprain itself and the investigations that were done and what symptoms they experienced and so on, the medical history. But we can also see other things about the patient. So we have information about the fact they have hypertension. We can see they're on a blood pressure pill for that. We know that they have suffered from anxiety. It looks like they're on medication for that. We know something about their social history. And we know various things about their general health. We also know what the plan is going forward. So it looks like it's pain management if we check these medications. And so actually we have a lot of information going on here. And we can imagine that if we're thinking about disentanglement, actually there are many factors here that we might want to disentangle. And this is a relatively simple report. Some patients are much more complex than this. So my challenge here is, whereas text actually in some sense is much more disentangled than imaging already, given that the words are at a quite high level and we already have the concepts almost, leaping out of us at us from the page. Because we're operating at that higher level and much more at the level that a doctor would, and they don't waste words, you'll see that this report is written in typical medical shorthand, so there aren't extra words going on. Actually, it's very information dense, and you're wanting to mimic the thinking processes of the doctor who is thinking through the various things that are going on with the patient and wanting to be able to make clinical decisions. So what characterizes EHR data? Well, it's very heterogeneous with different levels of abstraction. So we can have simple numerical values from lab tests or ECG, that kind of thing, through to these higher semantic data such as words. We can have variables like blood pressure and cholesterol level, through to more complex concepts like diagnoses or risk scores. So single numbers that actually contain a lot of information because they've been computed from a bunch of information, but in one number they can tell a doctor something about the status of the patient. There's a mix of structured data and unstructured data. So text is clearly unstructured, but we have much data which is already in structured form. So medications and prescriptions, lab test results, demographics, and so on would already be in structured form. We often have data which is sparse or missing. Sometimes we can infer what the missing data might be using our expert knowledge. And the data may be static, so for instance, demographics, or it might be time varying. So we might have measurements at different points in time. For instance, vital signs measurements or lab test results at different points in time. And in general, so alongside the imaging, actually, we still have lots of what we could call modes of data or data types within the electronic health records, so demographics and clinical notes and medications and so on. So we have a very rich source of information, but it's messy. So why do we want to do this entanglement? So we want to be able to separate different factors, and similarly to an image that might consist of disease factors, we might also consider treatment and lifestyle and patient factors. And actually, that tends to be in a much more holistic way. We want to align different modalities. So if we can extract representations, similar representations from text as we can extract from imaging and also from other data modalities. And if within the text we can also align, so often a concept might have the same, different names, I should say. So we might see diabetes, or we might see the abbreviation DM, or we might see that a patient's on insulin. So there's lots of ways to say that a patient has diabetes. And what we're wanting to do is align all of those in the structured data and the unstructured data, and across text and imaging and so on. And once we can get that standard structured representation, actually we can start to inject domain knowledge. So we already have knowledge bases which have been built up over many years. And we already know something about causal relationships. We know something about hierarchical relationships between different concepts. So we know that cardiovascular disease consists of, for instance, both stroke and MI. And we know that disease might be treated with a medication, not the other way around, and so on. And actually, we can start to infer variables that are missing using our expert knowledge. And if we look closer to the models, so similarly to the way that we would use content style images, models in imaging, we can use the same kind of models in text. So we might be interested to transfer style, and we might increasingly be interested to be able to phenotype diseases and disease subtypes. And if we can achieve this entanglement, we can do a variety of tasks, from error detection and diagnosis and stratification through to prediction and prescription. So here is an example of a task where we wanted to take text and we wanted to be able to predict the ICD codes which were assigned on the basis of the text. So these would be the diagnoses in the text. And in this case, a helpful technique for building the model was to actually make the structure of the model mirror the hierarchical organization of the concepts. So what we were able to do was say, well, in this case that we're showing, we've got a code which is brain metastatic disease. And so we know that at the top level, we've got a metastasis going on. So we've got a cancer going on. We know that it's a metastasis and we know its location. But we can share the code metastasis with any other metastases, and we can share the information that differentiates that cancer. We can share the cancer information, then we can differentiate to discover it's a metastasis, then we can differentiate to discover it's a brain. And we can see that at each level, in the way that we have organized our model, actually the attention is picking up on the differentiating information only, and it's able to share the learning for the levels above. So by using our knowledge, we've been able to design the structure of the model so that we can do more efficient learning. And this gives better results for rare codes. And you can see that when we go and look at the representation space, also now the representations are organized hierarchically in the same way that the codes are that we use for learning. Here's an example of text generation from images. So we talked about report generation a little bit earlier. In this case, we are making use of the fact that we know something about what concepts should be reported on in the imaging, from the imaging. So there are a couple of papers out there that have not simply gone image to text, but have actually supervised the prediction of pathologies and other keywords, which they automatically discovered in the radiology reports, which are the ground truth. And in this way, they now still use the imaging as an input for the text generation, but they also use the tags that have been detected. And this way we can do explicit supervision of concepts that we know to be important. And actually, I think there's a paper at MICI this year that tried to do something similar, but in an implicit way. So did latent variable inference. We might want to do style transfer. And this is a paper that shows how style and content in this case have been described as form and meaning. And they've been able to convert between text, which sounds Shakespearean, through to, or rather convert to text which sounds Shakespearean from original text. And we can consider that this might have application if we think about the letters that are written between doctors and we want to produce versions that are patient friendly. Actually, if we could convert from technical language into simple language, that would have interesting practical application. And next thing I want to talk about was disease subtyping. So as we move forward, we're interested in being able to stratify patients and thus make decisions about what treatment will be best for them as we move towards personalized medicine. And here, a very simple factorizing technique took the original clinical concepts and was able to identify different phenotypes of patients who would respond to different types of treatment. And although this didn't involve deep learning, actually it was explainable, which was really nice. And here I have an example of a deep learning technique which took the original data, so they turned text into structured data, but it was a very rich vocabulary of clinical concepts that they were expressing the text in. And using an autoencoder, they generated patient representations. And actually, once they then separated those patients into different subgroups, they were able to characterize those subgroups by their outcomes or symptoms, which were clearly related to outcomes. And so this showed a lot of promise for ultimately being able to personalize information. And finally, here are some examples as we move towards wanting to make predictions about patients and causality. So on the left, I'm showing a paper where they were actually looking at retrieval of texts, and they explicitly separated the text into the aspects of populations, interventions, and outcomes. And then when they wanted to retrieve on the basis of those aspects, it gave better performance. But of course, if we can extract according to useful dimensions, we can then aim to either discover or quantify those factors. And that's going to be quite important when we're looking at causality. And on the right, we can see that when you're able to take causality into account, actually, you're able to outperform the doctor's estimation. So in summary, electronic health records have been around for a while, but actually patients and clinicians haven't yet seen enough benefit. And if we can use machine learning techniques to help simplify and streamline the data and bring it together in a cohesive way, then we'll be able to open up exciting possibilities for phenotyping, prediction, and just better machine learning. Thank you. Oh, dead on time.